All right. So we have our number line. Back to our number line. We're done with the circles. And way back they had the natural numbers because we were collecting and farming and growing chickens and all kinds of stuff, and you can count them. Natural numbers. Then philosophically there was the concept of nothingness, and they wanted a quantity that they saw it as a quantity and wanted a number to represent that quantity, and 0 got added. Then there was the trading and owing something to someone else, and negative integers were not created, they were always there. We just needed to represent the concept of owing someone something. Then we had pieces of bread, loaves of bread, and we wanted to split that among many people. Cutting one loaf of bread that I usually counted here on the integers into smaller pieces, a portion of a whole, and fractions came to be. So there could be 1 1/3, if I do mixed numbers, and whatever. There's many fractions, right? Many, many fractions, filling the number line, growing on this set of numbers. So the integers with, well, they include the fractions, really, because you can write 2 as 2/1 and see it as a fraction, which is not a very complicated fraction. The integers with the fractions, we'll say, are called rational numbers. Why rational? I don't really know. They're rational. You can reason with them. They make sense. Rational numbers. So then the Greeks were all about, around 2,000 odd years ago, they were all about geometry. They see all these shapes and make buildings and draw drawings and all kinds of things. And they wanted to prove properties about these geometrical figures that they saw and so on. So then one of the big ones were Pythagoras, and among the many things that he did was looking at a triangle that make a 90-degree angle here, and let's call this one, I guess, A here for that length, B and C. Now we're not doing the geometry module until next semester, for those that will continue, but I need it for this one. And he proved, there are many, like hundreds of proofs for the relationship between the lengths of these sides. You can prove it, it is a fact. And even the Egyptians, when they built the pyramids, they knew about this. They didn't know about it in general, but they made a rope with knots, and a certain number of knots, 3 and 4 knots, and the side there, the hypotenuse, is 5 knots. And they used that to build the pyramids, among many other things, of course. But it was part of a bigger general property of these right-angled triangles. So no one questioned that. You can prove it in many ways. Look it up. There are like hundreds of ways to prove it. And maybe in the geometry section we will look into some of them. So Pythagoras was very well known, very popular. He had a school of followers that it was bordering on, not a cult, but more of a religion almost than just science, because they believed in these things so much, and they believed geometry explained the universe completely. So that means that if I make, let me just see my space here, if I cut a piece of rope, and let's say I make it length 1, whatever your unit may be, and I cut another piece of rope and I lay it there, also length 1, and I make sure they make a 90-degree angle. Then I have a lot of rope. I lay a rope here across so that it touches these sides. I cut it off, then I have measured a length here. Let's call it C, so it fits with that. I have a length. I've made a length. It's a measurable length. That means there has to be a number that represents that length. So here, some number must represent this length. Now at the time, the Greeks sort of formed schools, and Pythagoras had his own school, and they believed at that stage that these rational numbers, that was it. There's nothing more we need. What could we possibly need? We break a loaf of bread into many pieces, fractions, explain everything. There are no quantities, no lengths, nothing that is not represented by a fraction here somewhere on the number line. And it was bordering on religious belief. There is nothing else. Everything in the universe, every measurable quantity corresponds to some fraction over here. With Pythagoras' theorem here, we can make a 1 by 1 triangle and we create a length. So that length has to be represented by a number. Let's say here. So, if we use Pythagoras' theorem, we have c squared equals 1 squared plus 1 squared. So c squared equals 1 plus 1 is 2. So now for convenience, we have to give a name to this number, right? And we name it the square root of 2. Just for convenience, really. So now they believed firmly that somewhere that number is sitting over here. I've measured it. I'm just giving it a name. I'm representing it like that. So now the question is, this quantity is some fraction. For some a and b, what are a and b? Because fractions are everything. There's nothing missing from the list of fractions. I just need to find the a and the b that correspond to that fraction. It sits somewhere over here. What could it be? Now, oops, I shouldn't erase that yet. Now, you can actually measure this, and depending on how accurate you can measure it, their accuracy was a little shaky at that time, of course. You measure it somewhere over here, somewhere. And depending on your accuracy, you can get more and more accurate. But try as they might, they couldn't exactly find the a and the b that would make this exactly equal. What is the fraction that represents that? Until someone by the name of Hippasus, who was a student, part of the Pythagoras school, he came up with the following argument. So let's assume that there is some fraction like that, right? Whoops, a and b. For some a and b integers. There's some fraction. I don't know exactly what it is, but let's just work with that. That's now an equation that I can work with to figure out what kind of relationship is happening between a and b. Well, then I can say 2 is equal to a squared over b squared. Now stop me if something doesn't make sense. I want you to sort of follow it, but there are little bits that may make you uncomfortable. If something is equal to something else, then the square of that is equal to the square of that. Because they're the same, equal means the same. So I can then say here that a squared, by multiplying both sides by b squared, that a squared is 2 times b squared. Now, this is really just for interest's sake. We haven't really talked about equations and things like that yet, so I am jumping the gun a little bit, but it fits nicely in this topic. So I'm not going to ask you to repeat this or anything, but it's really good to see. It's one of the biggest things in math when you look at the history. So what does this mean? This means, if we understand our divisibility, this means that a squared is divisible by 2. A squared is an even number. You can say it like that too. A squared is even. Because it's 2 times something. I don't know what that other something is, but it's 2 times something, and 2 times something is an even number. It's divisible by 2. Because this number can be written as 2 times something. 2 is a factor of that number. 2 divides into that number. Now, you can convince yourself on the side that if I have a number times itself that's even, that number can't be odd. 2 odd numbers make another odd number. So, let's say here, A itself must be even as well. The only way A times A is even is if the number itself is even. There's no other way. If it was odd, 2 odd numbers would make an odd number. Only 2 even numbers can make another even number. And A squared is A times itself. So A itself is even, and that means it's divisible by 2. Now, what is the definition of divisibility? There is a quotient. There exists an integer, q for quotient, such that I can write this A as, when I divide 2 into it, I get my quotient, and I get a 0 remainder, because it's divisible by 2. That's what divisibility meant. When I divide it in, then I get a 0 remainder. All right? It's not going to be long. But it's so historically important that whether you remember it or not, you should see it at some point. Okay, so I don't need this, right? I don't need the 0, because it's just 0. So now, putting that back in, A is the same as 2q. Putting it back in over here, I can replace A with 2q. So, 2q, everything squared, is 2 times b squared, because A is the same as 2q. Now, if I simplify that, this is 4q squared equals 2b squared. Now I can divide both sides by 2. So I'm going to swap them around. B squared, excuse me, is equal to 2 times something. I don't really care what the q is. It's something. But that means that b squared is even. Let's say here, therefore, b squared is even. And the only way b times b is even is if b is even. And so b is even. I mean, divisible by 2. So it seems like we haven't gotten anywhere, but we've gotten somewhere very important. I'm going to leave the first line and make space like this and continue over there. So what does that mean? We had A is divisible by 2, and B is divisible by 2. Both A and B therefore have 2 as a common factor. And I can assume from the start here that whatever fraction representation I have of square root of 2, that this is in simplest form. need it simplified already as much as I can. But now I found that they have a common factor, 2. So A over B is not in simplest form. I can simplify it further. Now here's the little thing that might present some problems. So I can simplify this fraction further. If I now go back and say, okay, I simplify it, cancel out the 2's, get a simpler fraction, and I go back here and say, okay, square root of 2 now is represented by that fraction. Now I do the whole thing again. It's again going to have 2 as a common factor. So it wasn't simplest, actually. Then I simplify it again. And it always has 2 as a common factor, which means this is not possible because it's never in simplest form. So my original assumption that I can find a fraction in simplest form can't be true because it's never in simplest form. It always has a common factor. When do I ever stop? I have to stop eventually by my understanding of fractions. So this is a contradiction, which means that there is now a logical argument, and this is probably some version of exactly what the passes did. Our contradiction makes us conclude that there is no fraction that is equal exactly the same to this quantity, this length. Meaning that if I look at my number line again, I have 0, I have 1, I have 2. Yes, we have a calculator and put that into our calculator. They didn't have anything like that. And at the time they believed that fractions, that was it. There's nothing else. There's no quantity that can't be represented by a fraction. Yet I found something. This guy cannot be represented by a fraction. That means there are numbers there, in fact many others, that the fractions don't cover. There are many other numbers, many other quantities that are not on this number line yet. And because they believed in fractions so strongly, when he went to Pythagoras and said, or the other members, and said, look, I can prove that there is no possible way to write square root of 2 as a fraction. It was such a revolutionary idea that they didn't want to get out because it would shake all their whole belief system, that they drowned it to keep it quiet. Because they believed, everyone believed so strongly in these fractions that there couldn't possibly be something else. But there is. And now, in fact, there are many other non-fractions that are measurable quantities. Many others. Actually, there are infinitely more of these other numbers than there are fractions. There are so many of them. So we now call, of course they couldn't have suppressed this information for too long, right? It's a fact. Eventually it's going to come out. It's just unfortunate that he wasn't really celebrated for that, instead the opposite. We call these other numbers that exist, we call them irrational numbers. Why irrational? The opposite of rational. The bad news is that they're a little messy and difficult to really write in as clean a way as fractions. But together, the rational numbers with the irrational numbers are called the real numbers. And luckily, there's nothing else missing. The number line is completely filled by these two sets of numbers. Every measurable quantity in the world is a real number. There's nothing else that's missing. So at least that's complete. It's unfortunate that someone had died to actually realize that. Now, a more convenient way for us to represent the real numbers, fractions included, is by way of a decimal number representation that everyone is very familiar with. But it took a long time to really establish that. So we use a decimal point to represent real numbers, when needed, efficiently. For example, if I have a tenth, there's nothing wrong with that representation, but another representation would be 0, because there's no whole portion to this mixed number, 0.1. If I have 3 over 100, 300ths, that would be 0.03. So as I go to the other side of my decimal point, the left side will be tens, hundreds, like we're used to. This will be tenths. Oops, that's not easy. Tenths. 1 over 10, or a multiple of that. Hundredths. Hundred, how do you spell that? Like this. Oops. And then so on. So it's very efficient using the decimal representation. And we of course teach that. But not really why is it necessary. Because now to cover all these, fractions are nicer decimal numbers in the sense that I have two types of decimal numbers that are fractions. Fractions can be one of two things in terms of decimal representation. It can be what we call a terminating decimal, in that past the point it's all going to be zeros and we don't write the zeros. Like our examples there. We call it a terminating decimal. But if I look at something like a third, how do I find the decimal representation? Your good friend long division is there to say today. I'm going to move it higher a little bit, because this fraction is really representing division by integers. So we have 1 divided by 3. I know the answer is less than 1. So 3 doesn't go into 1. So I'm going to add a decimal 0. So 3 goes into 1 0 times, and then I haven't used anything. Now I see this as a 10. 3 goes into 10 3 times. 3 times 3 is 9. Take it away. I'm really subtracting 1 minus 0.9, and I have 0.1. Now you don't have to think about the zeros, just like we don't in the normal long division with integers. Now 3 goes into 1. No, I can't do it. I'm going to add another 0. Bring it down. Now I have a 10 again. 3 goes into 10 3 times. 3 times 3 is 9. Take it away. I have another 1. Bring down another 0. And you'll see I'm going to keep doing the same thing over and over and over and over, and I'll never stop. So I can also have fractions that in decimal form are non-terminating, repeating decimals. Oops. that, yes, they never end, but there's a pattern, and once I find the pattern, I can write this as soon as I have a portion that repeats, in this case the 3 repeats forever, I'll put a line over it. Some people use a dot. Oh, the dot's a little, a line's a little better. To say that portion gets repeated forever, so I don't have to keep writing 3's with dots or anything like that. That's a little more precise. So fractions can be one of those 2 things. And of course, if you think about what could happen, there's something missing, which is all the decimal numbers that don't ever stop and don't ever repeat. There's no pattern that ever repeats. So these are, of course, rational numbers, fractions. Rational numbers. And the irrational numbers are the non-terminating, non-repeating decimals, like square root of 2. That its decimals go on forever. There is never a pattern. Never a pattern that repeats. Pi is another one that we'll look at when we come to geometry. In fact, among many others, any square root of p, where p is a prime number. Those are very easy irrational numbers to come up with and prove that they're irrational. Not pi, the other one. Square root of 3, 5, 7, they are all non-terminating, non-repeating decimals. And they're, of course, much more difficult to find. So now the question that remains is, how do I go back and forth between a decimal version of a rational number and the fraction representation? Now I don't have my book. This is where you come in. Handy helper. Exercise 1413. First, given a fraction, how do I write the decimal version? Now, they're not going to be irrational numbers. It's either going to end at some point. My long division will have a 0 remainder, or I'll see a pattern enough that I can say what the decimal representation is. So this is 5 divided by 20. See, 20 doesn't go into 5. So I add a decimal 0. 20 goes into 50. How many times? Twice. 2 times 20 is 40. I don't see the decimal point. It is there, but I don't think of it. I see 50 minus 40, which is 10. 20 doesn't go into 10. So I need another 0, and then I have 100. It's not actually 100, but I see it as 100. 20 goes into 100. 5 times 20 is 100. And I have no remainder left, and then I stop. So this is 0.25. So I picked an easy one to start with. So you do not simplify the fraction first, you take it as it is. So the decimal representation of 5/20 is 0.25. What's the next one? 6/25. What is the decimal representation? So you really can't feel bad about long division. Without long division, what would we do? We need long division. It's just unfortunate that it has a bad name, that long is in the name. It's just unfortunate. It's not long, that wasn't long. It should be nice division, short division, fun division. Fun division, oh, that's a good one, I like that. From now on, this will be called fun division, because it sounds like one word. Fun division. 25 goes into 6? No. But maybe 60. 25 goes into 60 twice. And I've used 50. Take it away. I have 10 left. That's not enough. Bring down another decimal. This they do early. Grade, I don't know, 4. 4-ish. 25 goes into 100. 4 times. 4 times 25 is 100. And I am done. So 6 over 25 is 0.24. Piece of cake. How many more do we have? Ooh, that's a nice one. 13 over 12. Thirteen over 12. Again, fun division. 12 goes into 13? No. No, it does. 1. I'm just kidding. 1 times 12 is 12. I have 1 left. I'm going to bring down a 0. So that still not enough, is it? 12 doesn't go into 10. So I'll bring down another 0. Make it 100. 12 goes into 100. Now, you've played the raindrops game. You've gotten to 150. You're comfortable with all this multiplication and division. So it shouldn't be a problem. 12 goes into 100. How many times? 8. 8 times. Remember, that's a 0 and that's an 8. Right? Lines up. 8 times 12? 96. 96. Then I have a 4 left there. I'm not done. It has to be a 0 before I'm done. It's going to be terminating. So I keep going, extend my lines. 12 goes into 4. No. Bring down another 0. 12 does go into 40. How many times? 3. 3 times 40 is 36. Then I have a 4 left. That is not enough. Bring down another 0. 12 goes into 40. 3 times. 3 times 12 is 36. I'm starting to repeat myself here. 4, 4, 4, 4, 4, 4. So I conclude the 3's will just keep going. So you do enough until you're convinced that the pattern is just going to keep going. And this is 1.083 repeating. What I want you to do is not listed. Do 1/7, just to see what the division looks like. And you'll see there's not one number that repeats, but many that repeat. But you have to just see what the division looks like. It's going to be a long, that's actually going to be a long, fun division before you're convinced that the pattern repeats itself. So sometimes I'll just have 1 digit repeating, sometimes I'll have many repeating. So I would say practice that one on your own, because it'll take a while for you to be convinced that I'm just going in a loop. All right, that's 1. Then, of course, the other side is given a decimal number, how do I convert it to a fraction? If it's a repeating decimal, if it's a terminating decimal, it has a fraction representation. What is that representation? I'm guessing it's 1416. I really don't know. Just repeat then, don't worry about it. 1414, did I do something wrong? No, just me. I just looked at it. 0.378. Now the method is totally different. No fun division, sorry. But it's a very clear method. And it's a method that starts getting me used to variables and equations. We're slowly crossing over to the next chapter. What I'm going to do is I'm going to say the following. I'm going to say, let's call question mark in a box. That's my symbol for whatever this is. It's the fractional representation for that quantity. I don't know what it is. Try to figure it out. Now I know it's a terminating decimal, so I'm going to multiply both sides by enough to get that decimal point right there. Now you will probably be teaching this one day. As soon as I multiply by 10, I move the decimal point. Move the decimal point, move the decimal point. So 3, so 1,000 times the number. I have to do it on both sides, right? It's the same number. But now this, I can write as 378. Multiplying by powers of 10 moves the decimal back and forth. That's the convenience of our decimal system. So, let me just write it again. 1,000 times question mark is 378. What is a single question mark? What do I do, rather? I have to divide it. Because, remember last time, a multiplication sentence can be converted to a division sentence. So I'm going to write it like this for now, just to emphasize that I'm rewriting a multiplication sentence to a division sentence. Maybe you're not quite comfortable with that, right? Let's go with 2 times 3 equals 6. How do I write that as a division sentence? 3 equals 6 divided by 2. So easy. Yet when we have slightly less comfortable things, we think different things should happen, but nothing different is happening. Think about where I put things. This one is now alone on the left. This one goes to the other side with a division. So any multiplication sentence can be written as a division sentence. Now division is just another way of writing a fraction. Now of course that wasn't mind-blowing information, but I want to get used to this method for how to get there, so that when things get a little less obvious and less familiar, I have a backup and I can still find the answer. Everything's easy if I've seen it before, but I need a backup method for when I'm not so sure. 0.08. I'm going to call it question mark. By how much should I multiply this number to get 8 on the right? 100. I'm pretty sure you're only supposed to give answers of 10, but I'm going to let this one go, because technically it is 10 squared. 100. To move that decimal point away from all the interesting decimals. Multiplication sentence converted to a division sentence. Therefore, this is 8 over 100. And now we're starting with simple things. Soon we will not. All right, hopefully the next one is a little more interesting because I'm running out of time. But we'll just pick it up tomorrow because 5.95. I don't want to skip any of these. 5.95. When I have this, I know it's not necessary, but a convenient way is to see this as a mixed number, which it is. It's going to be 5 plus 0.95. I don't need to do it in this way now, but it's going to help me for the repeating decimals. So I might as well be consistent in my method. So this is going to be 5 and a little fraction. So I really only care about the little fraction. Call that question mark and try to figure out what that is. Now it's very similar to that. but I'll do a few steps here. I'm going to multiply by 100 again to get 95, to get the decimal point away from all the fun decimals. And so, question mark, I get by converting the multiplication sentence to a division sentence. And therefore, this is 5 plus 95 over 100, or the mixed number 5 and 95 over 100. All right. So you don't have to, you can do them all in one go, but it doesn't work for the next bit, so I don't want to bother. I want to always do the same thing. When I let these methods help me as a backup, I want to be consistent. Always the same steps, because that gives me security, comfort, confidence. It's always the same. And I just want to do the following one, which I guess I should have done first, but and we want to write this as a fraction. Now that method is a little bit more involved, I guess, but a very nice introduction to a systematic approach to doing something when it's not obvious how to convert this or why the fraction is what it is. Yes, if I've seen it like 10 times, I get used to what to do, and I see patterns, but that doesn't explain why it is like that. So my method is going to be a sequence of logical steps where I say I'm looking for something that represents this quantity. So the equal means it's the same. It's the same quantity, but different representations. So there's a fraction hiding behind this, and I don't know what it is. Now this is a repeating decimal. The 4s repeat all the time. So if I multiply both sides by, well, if I multiply the number by 10, this is the number and this is the number. So multiplying both sides by 10 would still give me an equal. But because I can see the right-hand side version of the number, I can write that in a slightly simpler way as 4.4 repeating. Because multiplying by 10 moves the decimal to the right one space. Now I still have a repeating decimal here that I don't like. So what I'm going to do is take away the decimal portion of it. Now the equal sign means that it's in balance. So I'm going to have to do the same thing on either side so I don't tip the scale, so to speak. But on the right, it's going to give me, still have an equal. On the right, I'm going to get a 4 because I've literally removed the decimal portion. But on the left, I don't know what to do. How else can I represent this 0.4 repeating? Well, from the very top, I have an alternative representation for 0.4444, which is the question mark. I just don't know what it is. So this is the same as saying subtract a question mark. Because question mark is 0.4 repeating is the same. So on the left, if I now have 10 question marks and I subtract one question mark, I have 9 question marks. That's perfectly intuitive. So what this is trying to do is it's giving me a stepwise procedure. Every step is manageable and fairly straightforward. And on the way, I figure out what this fraction representation is. So now, I'm going to squeeze it in here, because it's too low. I have a multiplication sentence. Converting that to a division sentence is going to be this. And division and fractions are very closely linked. There's just alternative ways of writing the same thing. And we can say the question mark is 4/9. These two things are the same. And I found the fraction representation of that repeating decimal. Some repeating decimals are easy, some may be less easy. But the nice thing about a stepwise procedure is that doesn't change. It's like a recipe. Follow the steps, and I'm going to get my answer. 2.72 repeating. Same thing here. 2 plus, really the challenge is finding that fraction portion. Not the whole number portion of the mixed number. That's not the problem. It's the other one. And now it's a repeating decimal. So my method is very similar. In that I'm going to try to find out that question mark that represents the same quantity. Problem is it's not a terminating decimal. But what I want to do is I want to get the repeating portion out of the decimal section. So I'm going to multiply by 100 because I'm moving the decimal point twice. The answer is not 72 because the 7272 keep going forever. So there are more 72s there that keep going forever. I've really just brought out one repeating section. There are still many. They never end. It's a repeating, non-terminating decimal. All right? Now, here, what do I have to subtract to get rid of that decimal portion? The decimal portion. Take it away. Take it away. But think of it as a balance scale. That equality says I have balance in my scale. If I have little things here, and I take one away, now the scale tips. I'm going to have to take the same thing away on this side too, in order for the balance to stay. The problem is I don't know what this is in relationship to this, but this tells me the question mark is the same as what I'm taking away here. So this guy is the same as question mark. So, on the right, what do I have? I have 72. On the left, what do I have? When I have 100 question marks, and I'm taking away one question mark. Little Timmy can even say intuitively, I have 99 question marks. Multiplication sentence, converted to division sentence, telling me question mark is equal to 72 divided by 99. Therefore, going up here, I have 2 and 72 over 99. Less obvious, which makes the backup method so much more important. Later on, we'll refine this to our variable and equation method. This is right now a little more intuitive before it gets converted completely. But it's that safety, that backup, where I don't have to look at 2.72 and know what it is. I have a method that systematically tells me how to get there. Another example that has different things repeating and padded with a 0 as well, just to see how I might be comfortable with this from experience. Play with that a couple of times and you see it's over 9 every time. This one, maybe less so. But the nice thing that gives me confidence and makes me feel safe, comfortable, is that if I follow these steps, I'm going to get the answer. There's no mystery here. I can explain exactly how I get to the answer. And without this, little Timmy asks, why is it 4/9? What do I say? It's not intuitive. From experience, maybe you get used to it, but that's not a replacement for understanding. I can explain exactly, yes, it's not the easiest thing to explain, but it can be done. So, my steps are the same. I'm looking for an alternative representation of that decimal quantity. So equal means it's the same, I just don't know what's hiding behind the question mark. Yes?
Are you doing the same one as in the book, or are you...
Did I not write it down right? Sorry, didn't write it down right. I was trying to do the same one, yes. Sorry. I have to get the repeating portion right, yes. Although the one I did have would have been a good one to do. We should maybe do both. So in that case, the 0, 1, and 2 are all repeating. Yeah, it's a good one to do the other one. We should do the other one. You see all the variations, and also see that the steps are pretty much the same. The only variation is in the 10, because that depends on what I have to move. Okay, so all 3 digits repeat. So, or then, I'm going to have to multiply by what? To move this decimal 1, 2, 3 places. I'm going to have to multiply by 1,000 in this case. To get, I'll say it here, 012.012 repeating. But I'm not going to write the 0. Right? It looks a little silly. Right. Need to get that repeating portion out. And remember, it still repeats over and over and over, that section. Now, what do we do next? I didn't actually clarify. Now let's do it like this then. 1,000 times my original decimal number. And let's try and do it exactly the same. The left-hand side stays the same, but I can simplify the right-hand side to 12.012 repeat. Okay. What do we do next? I want to get rid of that decimal portion. Now it's obvious what I have to take away, the decimal portion. I like the 12. 12's okay. I want to get rid of those decimals that never end. But I have to do it on both sides in order for the equation to be balanced. The right-hand side is going to be totally fine, because I just have a 12 left. That's why I chose that to subtract, so that I just have a whole number left. But here it is not as obvious what the answer is going to be until I see, well, 0.012 repeating, which is what I'm taking away, is the same as the question mark. So I can replace this with question mark. And I'm still doing the same thing. I have 1,000 apples, I take away 1 apple. 999 apples. Multiplication sentence, convert it to a to a multiplication sentence, and that tells me question mark is equal to 12 divided by 999, or in other words, the division is very closely linked to fractions. And that's just an alternative representation. And I can go up here and say the fraction representation of that is 12 over 999. Yes?
So at the end, when you turn the multiplication sentence into division, could you just write, like, on one side, divide, like...
I will say, I am assuming that you have zero knowledge about variables and equations. So given that, we don't know about simplifying equations at all. If you do, then yes, you divide both sides by 999, yes. But depending on your memory or your experience, I've learned to not assume that. And not everyone likes variables and equations at all. So I'm suddenly starting to head that way. Yes?
I understand it's like apples and stuff like that, whatever, but the 1,000 times the question mark,
Yeah.
you're taking away a question mark, why do you still have a question mark?
Because I had 1,000 of them.
Okay, but like, it's
And I'm
not
only taking
one
away
though.
one. Hmm?
Like, the question mark isn't one represented,
No, it
question
is
mark
one.
is
It's totally one.
0.012.
One of these is what I'm taking away. Question mark represents this. I'm taking away this exactly. So I'm taking away question mark. Well, you could also say I'm taking away one question mark. You can totally do that. Because a single question mark is equal to this quantity. Now I have to look at it as one, because what I'm taking it away from is much more. I have 1,000 of these. That's what multiplication means, right? If I have an object and I multiply it by 1,000, how many objects do I have? I have 1,000 objects. No?
No,
It's okay if it's not. No,
That's
you
so
don't.
funny.
Why do you think it's funny? Funny ha-ha or funny?
It's just weird taking away a question mark from a number.
No, not from a number. From more question marks. Should I line them up?
But you still have a question mark.
Yes.
Ah, there we go, that makes more sense. No,
Because I had 1,000.
Yeah, yeah.
Oh, did I not say
Good.
that right?
No, we're good.
Oh.
That makes a lot more sense.
Right, oh, so the lining up was the issue?
Yep.
Oh, okay, okay.
So, yeah.
I see. Little things like that that I don't think of, absolutely. We have to say something. Yeah. Right, no, I'm not taking it away from a number because I don't know what the number is. Any other questions? Yes.
So you have the 999 times the question mark.
Yeah.
Equals 12.
Yeah.
Why does it flip to division?
So, we said, let's take easier numbers. We had our example, 2 times 3 equals 6, right? And we observed that I can write any multiplication sentence like this into a division sentence. And, for example, this would be 3 equals 6 divided by 2. So any multiplication sentence has another version which essentially has the same information, just with a division instead of a multiplication. Now how do I shuffle these around? I keep the one here on the right, and this guy moves to the other end with a division, which is exactly how I reordered this. This guy moves to the other end with a division. But when we have larger numbers and question marks and weird things, it's maybe less obvious. But any multiplication sentence can be rewritten as a division sentence. Like that, for example. There are other versions as well. And in that way, I'm doing it that way because I'm not assuming you know how to simplify equations yet. We'll come to that. But you don't need it. You don't need any knowledge of variables and equations to do this. We are doing it in the background, but we don't need to think of it like that. So I can explain something like this to a grade level that has no idea of what a variable and equation is. They actually introduce variables very subtly, very early on. You don't call it a variable. I do want to do this one while I'm thinking of it. It was a little accident, but it might have been a good accident. Might have been a good accident. So let's see, we need to practice this, right? Clearly this is not a very comfortable thing to do. Maybe because it's just new. New things aren't always comfortable. But the logic behind this is incredibly useful. That what if my intuition isn't very good, and my intuition is terrible, terrible. What do? I need a systematic, logical approach to get me to the answer. That is what we're trying to develop. Okay, so now only the 1 and the 2 repeat. The 0 is just there for fun. The 0 doesn't feature any further on. It's going to be 1, 2, 1, 2, 1, 2, 1, 2. But if I'm going to get a method, this method better work always. So what do I do now? Well, look at this number. I need to move the decimal again 3 places, though. Right? Now, let's just be clear here. You're not going to love this. Just know that's going in. So let me know if something's not good. So I'm going to have to multiply this by 1,000 in order to get the repeating portion out. This is what I have. Multiplying by 1,000. I'm just going to move this a little bit so I have space for the 1,000. And I want to keep everything in balance, so I have to multiply 1,000 on both sides. On the right, very clearly, I get 12.01, no, not 0.1, 12 repeating, right? Because that's the only repeating portion. These are 1, 1, 2, 1, 2, 1, 2, blah, blah, blah. So once I, shift it, I have just 1, 2s everywhere. The 0 was only there in the beginning. And I have my 1,000 question mark apples. Now it was a slightly trickier decimal to begin with, so I need to just watch out for this step. This is really the step that's complicated, the subtraction step. What am I subtracting to get rid of the decimals? Looking at this, what should I get rid of? 0.12 repeating. I want to throw the decimals away. That's always what I'm trying to do. So that I can get to my fraction. Fraction is integer over integer. So I want to do it on both sides. So that everything's in balance. So on the right, we had a so. No, I don't know what that. Sorry, yes. On the right, I'm clearly going to get 12. Right? What do I do on the left? I've gotten used to always doing the same thing, yes, but there are slight variations here. I've gotten used to always subtracting 1 question mark. But now a question mark isn't exactly what I'm subtracting. These do not look exactly the same. They're close, but they're not the same. What is this? It is 10 question marks. It is 10 question marks. Because how do I go from this number to this one? I move the decimal over 1. That corresponds to multiplying by 10. So on the left, I had 1,000 apples. I take away 10 apples. I have 990 apples. Yes, it's confusing in the beginning, but you have to commend math for giving me a recipe to get there. I just have to understand the recipe. So now I have a multiplication sentence that I convert to a division sentence. That's always going to be the same. So the only variation is in that subtraction. Because different numbers require slightly different things. And so the question mark is also a fraction representation. And I can go back here and say it's 12 over 990. And if anyone asks why, yes, there could be difficulties in one of these steps, for sure. But once you get over those difficulties and get comfortable with what we're doing here, this clearly explains systematically in little steps why that is the fraction. So there's a little catch here to watch out for. Questions? Not sure? Or very sure?
You do number 6.
Oh, we'll do them all. Did we do 5? Yes. Then I inserted this one. Now 6. 2.04. I wasn't going to skip them. When it's a little newer and more difficult, we have to do more. And that's okay. Repetition is the key here. What was it? You know, I just looked at it. 2.04. Now, we said this yesterday, that if I have a whole number portion, this is really representing a mixed number, right? It's going to be 2 and something over something. That's not a division symbol. But I can write it like this. And the only issue is the fraction portion, not the whole number portion. This method doesn't work if I keep the 2 with it. I'm only interested in the fraction. It's not that it doesn't work, but it's unnecessarily complicated. So really all I need to figure out is what is this fraction portion. Then I can put it back and say it's the mixed number 2 and whatever fraction it is. So you don't have to do the whole thing, only the part that I'm interested in. So what do I do next? The nice thing about the recipe, why it gives me confidence and makes me feel comfortable, is I'm always doing pretty much the same steps. Multiplied by 100. I'll emphasize it. And then simplify the right-hand side to 4.04 repeating. I needed the whole repeating portion in front. It doesn't work as simply if I have the 2 here. It doesn't work as well. So let's not bother. There's no need for that. Because the 2 is not my problem. It's the actual decimal portion that's my problem. So, did I have a so? No, I didn't have a so. I'm subtracting 0.04 repeating. That is, thank goodness, the same as a single question mark. So there's no real complications there, luckily. So I have 99 question marks on the left and a 4 on the right. Multiplication sentence converted to division sentence like so. And I therefore have 2 plus 4 over 99, or the mixed number 2 and 4/99. So the 2 was never a problem. Why make it a problem? If I add it to my recipe, it's just going to make the recipe complicated, and I don't need that. Questions, comments, concerns? Do I dare ask for a compliment? Probably not. Try to make this as easy as possible. It is still math, and it has its own challenges because it's not as familiar. Any thoughts you'd like to share? Do 10 of these and you'll see it's really not that bad. Just like anything else. Do enough of it and you get used to it. And with that comes, the difficulty lowers naturally by repetition. That's the nice thing about math in particular. The more I do it, the easier it gets. That's not really true for other subjects. I can write 1,000 essays. It's not going to get any easier. Or I'm not going to get any better. But that's just me. All right, lastly, I just want to mention something about rounding, because not everyone knows how to round numbers, and we really should. If I have my places to the left and to the right of the decimal point, and I want to round to the nearest, let's say here for example, let's just do it by example. We've got 14.15. I have 146.08. 146.08. And not much else. I want to round it to the nearest 10. To the nearest 10. 10th is this one, this position. What I do is I look 1 to the right of that position. That number is going to determine, is this closer to a 0 or closer to a 1? And how I decide that is if this is 5 or above, 5 to 9, then it means this number as a whole is closer to the 0.1 than it is to the 0. So it's an 8 in this case. So the rounded version, this is number 1, 146.1. If that was, so let's say 5 to 9, increase the decimal or digit by 1. If it's 0 to 4, then keep the decimal or the digit the same. So for example, if I want to round to the nearest 10 and this was 0.34, the 4 tells me keep the 3. It's not large enough to push it over to the next one. Okay? 2 is 4.589. $4.589 and something else. To the nearest 100th. Well, that's 100. The 100th position. I look 1 to the right, which is this one. It has a 9, so I increase this by 1. So it's 4.59. Many are happy and comfortable with rounding, but not everyone. So I just want to briefly mention it. What do I do? Oops, not do, 3. 702,696. 702,696. To the nearest unit. Where is the unit place? This guy. Look 1 to the right. It's among the 5 to 9 digits, so I increase that by 1, and the answer is 703. Now, yeah, that rounding is common. So I look always to the one on the right of the place I'm rounding to. Last one, 42.7. Not that common to round to the nearest 10, but I guess it could happen. 42.7, I'm trying to round to the nearest 10, which is this guy. Look to the right. That is small, 0 to 4. So the rounded value is 40. Any questions on rounding? It's very simple recipe. Much simpler than the other one we were looking at. So you shouldn't really encounter much resistance when you teach little Timmy to round. It's pretty straightforward. But I just wanted to make sure everyone is comfortable around their numbers. Questions, comments?
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.